Okay, this is lesson 5.2b. You should be watching this after lesson 5.3. It's mislabeled as 5.2b. It could fit with 5.2, but realistically, if you're watching it in sequence, it should come after 5.3. The idea behind this lesson is it's to discuss the idea that rational functions can cross asymptotes. Asymptotes are things that behave, or functions behave around, and one of those types of behavior is crossing. It can't cross all types of asymptotes. It can cross horizontal and oblique asymptotes, and sometimes it can cross those asymptotes more than once. Ones that it's not going to cross are vertical asymptotes. So what I've done here is I've shown two examples, one of crossing a horizontal asymptote, and then the second example is crossing an oblique asymptote. Let's start by looking at what it looks like when we cross a horizontal asymptote. So I've done a little bit of the work for you already. We have our rational function, 1 minus x over x squared minus x minus 6. And since the degree on the bottom is larger than the degree on the top, we know that we have a horizontal asymptote at y equals 0. As long as the degree on the bottom is bigger, it's always going to have a horizontal asymptote at y equals 0. If the degrees are even, that's where we have to look at the ratio of the coefficients on the largest degree x term. But that's not the case. In this one, degree on the bottom is bigger, so the horizontal asymptote's at y equals 0. If we factor the denominator, we would find our vertical asymptote. So I'm going to do that really quickly. If we factor that denominator, we would have x minus 3 and x plus 2. And the roots of these, x equals 3 and x equals negative 2, are your vertical asymptotes. So we have three types of discontinuity. We have two vertical asymptotes, one horizontal asymptote, and I've graphed those asymptotes on an axis over here, and I've already done the work on the behaviors around those asymptotes. So the behavior around the vertical asymptote at x equals 3, from the left side we're going up, and I've graphed that here. On the right side, so plus, we're going down, so I've graphed that here, and I found those by just plugging in values really close to 3, 2.99 for this one and 3.01 for this one, and I saw what the sign was on the y value I got when I plugged it into my original function. I did the same for the vertical asymptote at x equals negative 2, and I got my behaviors, and I've also done it for my horizontal asymptote. For the left side, I plugged in a very, very large number, like 1,000,000, and I got a number slightly under 0, like negative 0.00001. And when I plugged in negative 1,000,000, I got a number slightly over 0, like 0.00001, slightly positive. So we know as x approaches infinity, we'll be approaching from the bottom, and as x approaches negative infinity, we'll be approaching from above. Now, if we were to complete this graph, it looks like this section of the graph will bend and go up. This section over here will bend and go up. But the question is, what's going on in the middle here? Usually, our arrows are together, like 2 down, and then it would bend and come back down, or you'd have 1 up and it would bend and come back up. The fact that we have 1 down and 1 up means that we have to get from here to here somehow. And here to here is across an asymptote. So we would guess that maybe we are going to cross that asymptote. The question is where. To find out where, you take your original function, f of x, and you set f of x equal to the horizontal asymptote, y equals 0. What's that mean? Well, we take our f of x, which is 1 minus x over x squared minus x minus 6, and we set it equal to the equation of the horizontal asymptote, which is 0. And we solve. Well, how do we solve? Multiply both sides by the denominator. That will remove it on the left side. We'll be left with 1 minus x, and 0 times x squared minus x minus 6 is also 0. So we're just left with 1 minus x equals 0. And if we add x to both sides, we get x equals 1. And this tells us that we cross our horizontal asymptote when x equals 1, because that's where our function is equal to the horizontal asymptote. The function at 1 is 0. How do we know? Well, we plug in 1 and solve, and we get 0. Therefore, f of x crosses the horizontal asymptote at 1, 0. So on our graph, that would be this point right here. Our y-intercept is -1/6, so that would be just down here. I could find that by plugging 0 in for x and solving. And so our graph is going to look like this. It's going to approach, and it's going to cross, and approach, and bend back up. So that's our middle piece. Since we don't cross the asymptote here, we can then assume that we're going to bend and go up. And since we don't cross the horizontal asymptote here, we can assume that we bend and go up. And doing this analysis of if the function crosses the asymptote helps you ensure that this behavior in this section is just going to go up to the asymptote and bend and finish below. If it crossed over here, it would have to cross twice because the behavior is here. It would have to go up and come back down and then approach. And that's possible, but since we did the analysis of whether it crossed or not and found it only crossed at 1, means it doesn't cross here, means it just goes through. Sorry, just goes through and finishes below. Same here, finishes here in the same section, but since we cross our horizontal asymptote at 1 in the middle section, we approach, cross, and then bend and go up. So that's an analysis of crossing a horizontal asymptote. Second example. Same concept, just a little bit more complicated because we have an oblique asymptote in this case. The reason we have an oblique asymptote is because the degree in the numerator is bigger than the degree in the denominator, and it's bigger by an order of 1. So it's 1 degree bigger. So when we do our polynomial division, we'd end up with a degree 1 polynomial, which is a line. Therefore, we have a line asymptote called an oblique asymptote. And I did the polynomial division, and we ended up with the line 2x plus 1. The behavior around the oblique asymptote you can find just like how you would find the behavior around a horizontal asymptote. You plug in a very large value for x and see what happens. If I plug in 1,000,000, I get 2,000,000 plus 1, which is 2,000,001. That's a large positive number, which means we're going to continue to trend to infinity. When I plug in negative 1,000,000, I'd get negative 2,000,000 plus 1, which is negative 1,999,999, which is a very large negative number, which means we're going down on the left side, up on the right side. The tricky part is you don't know if your behavior is going to be above the asymptote or below the asymptote. You just know that it's going to go up in this section, and you know it's going to go down in this section, but you don't know, again, below or above. How you can find out is an analysis as to whether the graph of our function f of x crosses this oblique asymptote. I've done the behaviors around the vertical asymptotes, and the vertical asymptotes come from factoring the denominator and looking for each root. There's 2 roots, -3 and 2, so we have 2 vertical asymptotes at -3 and 2, and I've done the behaviors around those vertical asymptotes by testing values around the vertical asymptote values. What I found was that at -3 on the left side, we're going down to -infinity. On the right side, we're going up to positive infinity. Now, since we're down in this section and we know the behavior around the oblique asymptote is going to also be going down, we need to decide whether the graph's going to go up and bend and it's going to stay in this little section down here, or if the behavior is going to be above and we're actually going to cross the asymptote, then approach from above. Likewise, in this quadrant, we don't know whether this behavior is going to be above or below, so we need to test to see if our function is going to cross the oblique and approach from below, or whether it's going to stay in this upper quadrant. Now, I've kind of ruined the surprise by actually putting that on there to show you that it is above, and the reason why is because when you test to see if it crosses, it doesn't cross at a value greater than 2. So that means that this section of the graph does look like this. And the function also doesn't cross at a value less than -3. So it does look like this. Where it does cross is actually somewhere in the middle here. And the only reason I can tell you that is because I've done the math already. And you would do the math and you would see that it does cross in the middle too, and we are going to do that math. But since around our vertical asymptote we had a behavior of up on the right side and down on the left side of our second vertical asymptote, the only way to go from here to here is to cross that line in the middle. So the question is, where does it cross? Well, we use the same idea. We take our function f of x and we set f of x equal to the oblique asymptote y equals 2x plus 1. So what's that look like? Well, our function is 2x cubed plus 3x squared over x squared plus x minus 6, and we want to set that equal to 2x plus 1. So how do we solve this? Well, we multiply both sides by the denominator of our fraction, which will eliminate on the left side. So I have 2x cubed plus 3x squared. And on the right side, we'd have 2x plus 1 times x squared plus x minus 6. And now we'd have to expand this out and collect like terms. I'm going to save myself a little bit of work, and I've already expanded it out. And our terms look like 2x cubed plus 3x squared minus 11x minus 6. And now we move our terms all to one side and isolate for x. So we've got 2x cubed on both sides. So those, when we move them to the same side, are going to add to 0. Same with 3x squared. Those are going to add to 0. And if I move my 11x over, we can start to isolate for x. We can do that by dividing both sides by 11. And we get x equals negative 6 over 11. If we take our equation of our line, or our oblique asymptote, and plug in negative 6 over 11, we will find the y value for where it crosses, which is negative 1 over 11. You could plug this into the original functions equation, but that's much more complicated than the equation of the line. Since the line and the function are equal at this point, you can plug your x into either the oblique asymptotes equation or the functions equation. But oblique asymptotes equation is much easier, so that's what I chose to do. And therefore we can conclude that f of x crosses the oblique asymptote at negative 6 over 11, comma, negative 1 over 11. Where would that be? Well, that would be slightly below the line. Let's say it's right here. So what's our function going to look like? Well, it's going to bend down, and it's going to cross here, and then it's going to cross down here as well. X-intercepts are roots of the numerator. So I'm going to do that really quickly so we can complete our graph. Where are x-intercepts? Well, 2x cubed plus 3x squared. If we common factor that, we get x squared and 2x plus 3. Therefore, our roots are x equals 0 and x equals negative 3 over 2. So negative 1.5. So we're going to cross here, and we're going to cross again at 0, but it's going to bounce off because it's of order 2. So our graph's going to go down, look like this, bend up, touch, and then bounce back down. And that's pretty funky behavior in this area here, but that is what it looks like. 2x intercepts, y-intercept, crossing the asymptote right here. So how do we test for crossing? You take the equation of your asymptote, set it equal to the equation of your function, and solve for a point where it crosses. And then make sure your function bends through that point through the asymptote. If it doesn't cross anywhere else aside from in the middle section here, you can assume that the function is going to bend and stay between asymptotes everywhere else on the graph. That's how we can conclude that the behavior is going to be above the oblique over here and below the oblique over here, because the function already exists in this section, so it's going to continue to exist in that section. It's not going to cross and cross above, because it doesn't cross here. It only crosses right there. That's our lesson on crossing asymptotes. Thanks for watching.